Alright, you're back with Mr. Klinkman. We are going to start working on the final goal of this section where we're going to be working on optimization problems. Alright, and we've already read the 3 learning goals where the third one is that you're going to apply techniques for finding extrema to solve optimization problems. And in fact, we've already worked on an optimization problem. And I want to show you 2 to 3 more optimization problems that you might encounter and just talk about the principles involved with actually trying to optimize some kind of function. And in particular, the next 2 problems that I'm going to show you are going to involve geometry in some way, because there's lots of situations where you can minimize or maximize, say, areas or volumes or that type of thing with geometry type questions. Now, I'd like you to go ahead and read through this problem, and then I'll show you what we're going to do to find the maximum area that the farmer can enclose for this particular problem. Now, the first thing we need to talk about when we're trying to figure out what is the maximum area that this farmer can enclose is we have to understand how he's enclosing this farmland. Alright? And instead he's having a rectangular enclosure. There's a river on one side, and so there's no reason to put a fence right here, because why would you need to fence something if there's a river right there? And then secondly, he's wanting to divide this into 4 equal-sized partitions. Alright, now you see the entire length for what he wants to enclose is x units long. That's the length. And then the width is y units. Well, every little line that you see here apart from the river is something that's going to be fenced. And we have 1, 2, 3, 4, 5 little vertical segments, if you will, that need to be enclosed. Alright, that's going to be important to us here in a moment. Now for the principles in solving an optimization problem. And perhaps the most important thing that you got to begin with is you have to know what it is that you're maximizing, and you have to be able to write some kind of function that will allow you to optimize, either maximize or minimize that function. Alright, now we're trying to find the maximum area that the farmer can include. And so one of the things that we have to know is, how do you calculate the area of this enclosure? Well, fairly simple, right? It is just a rectangular enclosure, and the way you find the area of a rectangular enclosure is you multiply its length times its width. And in this case, that means x times y. Alright, but it turns out that's not going to be enough for us to find the optimum area, because, well, we don't know what x or y are, for one. 2, we're trying to describe the area in terms of 2 different variables, and what we really need to do is be able to describe somehow the area of this rectangle in terms of just one of those variables, either in terms of x or in terms of y. Alright, so we're going to have to use the other information in this problem. Bet you realize that already. And we're going to have to use that in a particular way to try to make it so that the area is either in terms of x or in terms of y. Now watch this. In addition to knowing that the farmer is dividing this into 4 equal-sized partitions, we know that he has 600 meters of fencing to work with. Okay, now that 600 meters of fencing has to include this, plus this, plus this, plus this, plus this, the 5 vertical sides, plus that 1 horizontal side of the fencing. And what that's going to be helpful for is this. We can make an equation that relates x and y with one another now, because we know that if we take the length, just that bottom side, and we add it with the 5 vertical segments here, the total of those fencing segments has to be equal to the total amount of fencing that the farmer is working with. So we can say x plus y is equal to 600. Okay, now remember, we were trying to maximize the area, but our problem was that we had the area in terms of 2 different variables, x and y. Well, what we can do is we can now use this equation that relates x and y with one another. in order to write one of those variables in terms of the other. In particular, what I'm about to do is I'm about to solve that equation for y by subtracting x from both sides and then dividing by 5. So we'll get y equals 5y equals, 600 minus x. And so y then would equal 120 minus 1/5 x. And now what we're going to do is we're going to take that value of y that we just discovered. All right, y is 120 minus 1/5 x. And we're going to come over to our area function that we're trying to maximize. And we're now going to be able to write it using only one variable because we can substitute in place of y the expression 120 minus 1/5 x. Alright, last thing I want to do with this for the moment is I want to go ahead and simplify it. Let's just say then that the area of this rectangular pin is equal to 120x minus 1/5 x squared. Alright, great. Now we have a function that we can work with in terms of maximizing the area. Now let's talk about what we've learned as far as trying to find a maximum or minimum value. We said that the maximum or minimum value of a function can occur at either one of its endpoints or at one of its critical values. Now we'll have to talk about the endpoints and so forth here in a moment, but you know that you find critical values through finding the first derivative of a function and finding out where the first derivative is equal to 0. So let's go ahead and do that. And of course, then that's going to tell us that the derivative of this area function is equal to 120 minus 2/5 x. Now let's finish finding the critical value, or critical values is what I would normally say, but there is only one this time, by setting that derivative equal to 0. And if you solve that equation, you're going to end up getting that x is equal to 300. Okay, so that's a critical value right there. Now the next thing I want to discuss with you really quickly is this. What is the domain for that area function? What are the possible values of x? Well, pretend for a second with me that we're trying to find the smallest possible value that x could be. Well, x is the length of that rectangle. What if the farmer didn't use any length? He just made all his fence width. In other words, he made this thing 600 meters tall, but he made it 0 meters wide. Okay, that 0 kind of describes the small boundary for what x is allowed to be equal to. So I could say that 0 has to be less than x. It can't actually be equal to x because then you wouldn't have the rectangular enclosure, but that is the smallest that x could possibly be. And now similarly, if I'm looking at what's the largest possible value for x, well, theoretically, the farmer could use all 600 meters, I think I said feet before, he can use all 600 meters of fencing horizontally and not use any vertical fencing. And if he did that, then x would be 600. Now it can't actually be 600 because, again, we do want a rectangle. We can't let the width actually be 0. But that describes the domain. All right. Or in other words, based on what we're trying to do, it tells me what the lower endpoint of the function is, and it tells me what the higher endpoint of the function is also. And so, if we're going to find out what value maximizes the area, we're going to have to figure out these three things right here. We're going to have to figure out what a of, and we're going to pick something close to 0 because we can't actually plug in 0 into that function. Let's say 0.1. And then let's say we figure out what a of the upper boundary is. If we plug the upper boundary in, well, we can't actually plug in 600, but let's just say it's 599. And then let's plug in the critical value. Let's figure out what a of 300 is. Now use your calculator, plug each of those values in for x into your area function right here. See what you get. And here's what you ought to have found then. If that length was as small as it could possibly be, which we just said, hey, what if that's 0.1? Well, then you would get approximately 12.0 square meters for your area, all right? If it was as large as it possibly could be, and I just used the 3 significant figure approximation for the largest, well, without saying 600 anyway, then when you figure out that the area of this enclosure would be about 119, or really about 120 square meters to 3 significant figures. If we plug in 300, if we plug in our critical value, then you end up with the area is about 18,000 square meters. Now, knowing what we know about finding the maximum values, that they have to occur at either the endpoints or at critical values, we know that we have figured out all the places where the maximum can occur, and it turned out that the maximum area occurred when x was equal to 300, or when the length of this fencing was 300 meters. Alright, now what the problem asks us for is the maximum area the farmer can enclose. And of course we can say that the maximum area is 18,000 square meters. Pretty nice enclosure. Another problem that you can be asked oftentimes with this kind of thing is, what are the dimensions of the enclosure that would yield the maximum area? And, well, that would be asking us to find out what are the length and the width, basically. Alright? Now think this through. If we use 300 meters here for the length, that means that the 5 times y has to be the other 300 meters, right? And so y would be equal to 60. So the dimensions of the rectangle that would give us this particular maximum area would be 300 meters by 60 meters. There you go. There's an optimization problem. We're going to look at least one more of those. This is something that is going to be very useful to you. All right, thanks for listening.